Okay, good morning all. Nice to meet you. I am Francesco. I belong to Enginesoft, and today we are here with Koji Yamamoto from Cybernet to present his webinar about multiscale.sim and in particular simulation for the manufacturing process of all solid-state battery. So nice to meet you, Koji. It's a pleasure to have with us, and you can start.
Thank you so much. Thank you for your kind introduction. I'd like to share my screen firstly. Please forgive me that I would like to switch off the video.
Yes,
because,
we see.
Because our network is very slow. So, okay, again, thank you very much for your kind introduction. Hello, everyone. I appreciate you participating today. My name is Koji Yamamoto from Cybernet Systems in Japan. We are ANSYS channel partner in Asian region and also developing some original CS software, which is embedded in ANSYS Workbench platform. We are collaborating with Enginesoft so that people in countries other than Japan can use it. Today, I will introduce an overview of the software, which name is multiscale.sim, and some use cases using all solid-state batteries as an example. I hope that my presentation can provide useful information for you. Here is the agenda of my presentation. The first topic is a basic background of all the solid-state batteries. I would like to introduce the internal microstructure of this product. I will focus on the differences from conventional batteries and the technical challenges for manufacturing. You will understand that handling powder material is important for this application. And then I will explain the specific manufacturing method. Our solution is designed to help the manufacturers of high quality all solid-state batteries to overcome the burden of trial and error from the perspective of simulation. I would like to motivate the need for our simulation technology by taking the deeper look at some of the challenges in manufacturing process that are barriers to achieving high performance. And each analysis technology will be introduced through several examples for each processes. What is important here is that the appropriate analysis method is different for each process, and the technology to seamlessly link them is required. I believe that our solution is effective for this purpose. So now let's get down to the first topic, which is about the background of all solid-state batteries. I guess that people in almost all manufacturing industries are currently in the situation where we have to aware of efforts to achieve sustainable society. Among them, in the transportational equipment field, efforts to replace conventional fossil fuel with clean alternative are attracting attention as a meaning of reducing the global environmental impact. For example, hydrogenated and carbon neutral fuels, which is called SAF in the aerospace industry, and finally electrification. This presentation is about the solution related to electrification, but when we look at the issues involved in realizing such solutions, we see that many of them are still caused by batteries. This is also including charging infrastructure, weight reduction, quality, and safety. Our solution focuses on helping to improve quality, but in terms of need for all solid-state batteries, the issue of safety becomes very important. The figure on the right shows the internal structure of the typical lithium-ion battery. The active materials in the anode and cathode shown here are the materials that store electrical energy. Ions are responsible for transporting this electrical energy. The ions move between electrodes as they are charged and discharged, enabling them to be reused. The pathway for the ion is the electrolyte, which corresponds to the area filled with blue in this figure. The problem is that this electrolyte is highly flammable. And as you can see the photo on the left, not only during car crashes, but even during normal operation, thermal runaway can accidentally occur due to unintended factors, leading to serious incidents in some cases. I am sure that you are aware of this through TV news or the media. On the other hand, the concept of the all solid state battery is basically very simple. Just replace the flammable electrolyte with a solid material that is not flammable. The figure on the right side shows the solid electrolyte that has been replaced by the yellow area. However, we can't achieve good quality even if we simply place this solid electrolyte in the bulk state between the electrodes. This is since solids cannot change shape as freely as liquids, and thus cannot provide good ionic pathways. So, as shown in the figure here, solid materials are crushed into pieces, in other words, powders, to obtain high liquidity. And it is filled inside the battery, and finally the products are made by pressing them. In order to improve battery performance, it is important to create a layer of solid electrolyte with a high volume rate and no voids so that ions can move well. And to have dense contact between the individual particles, controlling them is almost entirely a matter of manufacturing process. Okay, so I'd like to introduce the concrete manufacturing process of the product. Although there has been no perfect manufacturing method yet, popular methods can be broadly divided into two types, that is dry and wet types. As the name implies, a dry process makes the product by manufacturing without the use of any liquids. The materials used in the wet type are similar, but the only difference is the inclusion of an additional solvent. Looking at the material, there is only one difference, but looking at the manufacturing process, there is a quite difference, as shown in the third column. Looking first at the dry type, it consists largely of mixing, filling, and pressing. An important point in dealing with simulation here is that the property of the material significantly change in this manufacturing process. This material has powder characteristics in the mixing and filling process. Powder have such unique behavior that they are considered as a phosphate, different from fluids, liquids, or solids. So it is important to apply powder-specific techniques when handling them in simulations. The compaction process also will behave like a powder immediately after startup, but as densification progresses to a certain degree, the behavior changes to almost solid. On the other hand, the wet process also starts with mixing, but unlike a dry process, the material at this time is a slurry state, where powder dissolved in the solvent. So it is clearly behaves more like a fluid. It then goes through the process of coating and drying, and then it returns to a powder. Both methods still have their advantages and disadvantages, but this presentation will focus on the dry process. As a last topic, I will introduce simulation technology of each manufacturing process for the purpose of battery performance evaluation. At this point, I'd like to introduce one of our unique solutions before proceeding to the detailed simulation technology. It is a technology called multiscale analysis, which is a technology that links a problem of different scales. It predicts macroscale material properties from the information on microscale. There is no clear definition of the small scale we are dealing with here, but it is generally on the order of nanometer to millimeter, and larger scale should be viewed as a larger scale than that. This is still a bit abstract. Let me give you an easy to understand example. Making medicine, although it is not matched with today's main topic, smallest scale corresponds to the structure of molecules and proteins. For example, assuming that drug used to treat a disease, the protein of the pathogen would be analyzed to design a molecular structure in the form compatible with it. This is directly related to the efficacy of the drug. On the other hand, one scale larger than that, also called the mesoscale, is a state of dispersion or coating if the drug is a powder form. For example, if you want to deliver a drug to intestine, we don't want it to be dissolved by stomach acid after swallowing. So the desired drug delivery can be achieved by coating. Then these information in small scale dominate macroscopic characteristics, which is placebo properties, efficacy, medicine side effects, taste are example for it. The same idea can be applied to batteries. From nano to micro order means molecular structures. It determines the material properties of the electrolyte or active materials. The mesoscale information is the structure of a powder in which the materials are mixed. It includes the mixing ratio of each material and the particle size distribution. And the macroscopic characteristics we can perceive is the performance of the battery itself. Electrical characteristics include internal resistance, charge-discharge characteristics, voltage, and so on. This must be the information you finally want to know. But in any case, without knowing information on the small scale, it is possible to predict macro characteristics. This microstructure of the product is highly dependent on the manufacturing process. So it is necessary to simulate each manufacturing process to predict the performance of the product. There are some important points that we must consider when selecting appropriate simulation methods for each manufacturing process. It is to clarify the factors governing the phenomena occurring in each process. By taking this step, it becomes clear which method we should employ. Here, material properties were adopted as criteria to decide it. The property is divided roughly into two types, which are mechanical and non-mechanical properties. Only the typical properties of each type are described here. Density related to weight of the particles, strength, which is the indicator of crackability, and rigidity, indicating the ease of deformation. Non-mechanical properties include the amount of expansion and contraction of a material during the charging and discharging process, and thermal and ionic conductivities related to heat and electricity, for example. And the horizontal axis shows the manufacturing process. And in addition to the three representative processes shown earlier, I have added a few new items in the upstream and downstream sections. Strictly speaking, all material properties affect any process, but it is important to identify only the dominant properties from the standpoint of saving computational cost. For example, if it is mixing process, strictly speaking, particles may be somewhat deformed during the process, but when measuring the degree of mixing, the motion of each particle is more important. So the density of the particle is the dominant physical property. The same can be said for filling, but once the particle enters the compaction process, deformation of each particle is significantly large and cannot be ignored. Based on the results of these considerations, a calculation method should be adapted. DEM is mainly appropriate for upstream powder problems, where particle deformation can be ignored, while FEM is appropriate for problems where particle deformation cannot be ignored, or where non-mechanical behavior needs to be evaluated. Anyway, let me give you a little overview of the methodology for DEM and FEM only here. DEM stands for discrete element method and is characterized by the discrete nature of the elements that makes up the system. The image below shows an extremely simple system consisting of 9 particles. Although each particle is in contact with a neighboring particle, they are not bound together and are basically free to move around without being significantly affected by the surrounded particles. So when the particle is subjected to a force, it can be basically move around freely, although of course it may collide with other particles. When particles are compressed from the tightly packed state, the particle cannot move, and the deformation should be becoming apparent. To analyze this state, DEM can also be expressed stiffness behavior. Rheological elements such as dashboards and sliders can also be included to easily simulate the viscous and plastic behavior of materials. In any case, it can be expressed as a macroscopic deformation of the entire powder system, but the particles retain spherical shape, and the deformation is expressed only by beating into them, so the microstructure is never expressed accurately. On the other hand, FEM is characterized by the fact that the system element is continuous. As shown in the figure, when the model is represented by 9 elements, the adjacent elements are formally connected as shared nodes, and force is transmitted to the adjacent elements. For example, if a force is applied to a part of the surface, the element will not fly away and will be transmitted to the neighboring elements. As a result, it will be possible to evaluate how the entire shape is deformed in detail. Stress and strain distribution in the system can be also observed in detail. Let me explain in more detail about the analysis flow to use DEM and FEM for this problem. As I mentioned earlier, the particle filling problem should be handled using DEM in terms of analysis efficiency. On the other hand, FEM can be used as a method for dealing with powder compaction problems when evaluating the performance of molded products. The microstructure after molding should be obtained as accurately as possible. At this time, the particle arrangement at the start of compaction is one of the very important factors. that will affect the results of the analysis. So the results of filling process must be reflected correctly. Our software, multiscale.sim, provides an interface to realize this collaboration. You can create solid model for powder by using other interface to spacecraft. After that, meshing with mechanical and perform FEM analysis. Since this analysis is a highly nonlinear problem, it is important to use an explicit method rather than implicit method. Apart from that, as you know, it is also necessary to experimentally prepare the material constants required for each analysis. The table above summarizes the test methods for this purpose. In particular packing problem, interaction between particles, especially the coefficient of friction and small adhesion forces, affect the results. These properties are generally obtained by single plane shear test or AFM test. Other material constants are also required, but only the representative ones are shown here. Particle size distribution can be directly measured in a variety of ways. In powder compaction process, the mechanical properties of particles are also important. A microcompression test is effective for this. In this test, a single particle is compressed. We can also handle small particle sizes on the order of several microns, and then obtained stress strain properties in this way were entered into explicit FEM analysis too. So let's move on to the specific analysis examples. I will start with the mixing process due to limited time. If only certain materials are uneventually distributed in some areas of the final product, the battery will naturally not perform well. So it is important to mix the material as uniformly as possible. The animation I am showing you now simulates the 3 different material powders being fed into the chamber and mixed by rotating ribbon. The mixing is color-coded to show the differences in materials for easy visual inspection. Although I do not show the concrete definition here, we use an index that quantifies the degree of mixing, which is called as the Rayleigh mixing index. The graph on the right side shows this index over the time. This index of unit value means a complete mixing. So we can see that it takes about 60 seconds to obtain good mixing state. This allows us not only to predict the time for complete mixing, but also to visualize the mixing in the chamber by coloring each material. Of course, it is difficult to observe in actual experiment. If the mixing is not going well, we can investigate the cause of it based on this information, and therefore take measures to improve the process. As you know, the analysis approach has a strong point in areas such as trial and error to improve mixing efficiency. These mixed powders are used in the next manufacturing process. This process corresponds to the application in the wet case, but in the dry case, it corresponds to the filling in the powder into the mold. This process is quite simple in practice, basically just pouring the powder from the top of the mold. However, from the phenomenological viewpoint, there is something somewhat special. Unlike previous process, there is almost no large external force during the process. What is important is that influence of small forces working between particles between apparent. These forces usually not need to be aware. This is commonly referred as the adhesion force, which is typically caused by, for example, electrostatic force liquid bleaching, or van der Waals force, and so on. Although not a single factor, adhesion models are provided by ANSYS Rocky to represent these factors, so that particle placement after the filling process can be predicted by taking them into account. Of course, to obtain quantitatively meaningful results, physical properties representing this adhesion force must be prepared. We are now collaborating with some university to conduct experiments to measure them. I would like to introduce a topic to identify these properties on another occasion. Okay, let me show you one simple example of the analysis. Powders with different particle size distributions were fed from directly above the rectangular mold. After feeding, vibration corresponding to tapping is applied in the left and right directions after powder is reaching the bottom of the mold. The leftmost figure shows the result under conditions of uniform particle size. The particles are randomly arranged immediately after they reach the bottom, but by applying vibration, the particles become regularly aligned in phase in the height direction, and the particles of the second phase are stably arranged in the concave region created between the particles of the first phase, eventually converging to FCC crystal structure. The other two animations are the results in the case of powder having size distributions. Bias distribution means that the probability peaks are more biased toward smaller than the Gaussian distribution. When smaller particles are mixed as a Gaussian distribution, they enter the gap created between the larger particles, so the final packing ratio is higher than for the uniform size. However, if too much tapping is applied, the smaller particles move in the direction of gravity through the gap between the larger particles, causing the smaller particles to accumulate below, eventually resulting in the segregation. Since the same amount of material is fed into all three conditions, comparison of the height of the powder layer shows that there is a considerable difference in filling rate depending on the particle size distribution. Voiding left in the electrode will not have any positive effect on performance, so it is better to obtain a structure with as high filling rate ratio as possible. And it is important to avoid segregation for stable quality of the final product. The final step in the series of molding process is compaction of pressing. Again, since deformation is more important than particle motion in this process, so the analysis method is using FEM is employed. Since the initial arrangement of the particle is an important factor affecting their results, the particle arrangement obtained in the previous filling process is converted to cathode data and reflected in the analysis model. As shown in this animation, the FEM considers the deformation state of individual particles. The results of the FEM analysis can be used for performance evaluation analysis, which will be introduced later. This example is for demonstration purpose only, but compares the result of uniform size distribution and Gaussian distribution, as in the case of filling. A bit of topic, but there is often a problem that arises when simulation is performed. That is whether the analysis results obtained here are really representing real problems. This problem can only be verified by comparison with experiments. But the reality is that it is difficult to measure the state of deformation in microscale, such as the animation we are seeing now. Therefore, it is also important to obtain the results that we can easily measure by adapting the multiscale concept introduced earlier. This is a stress strain curve as macroscopic property shown on the right. Since the slope of this curve is almost equal to the stiffness of the material is very soft and flexible in the small compression ratio state. But the stiffness increases rapidly with increasing compression ratio. This corresponds to the transition of the material from the powder state to solid state. This problem is solved by explicit method using anti-Ceres dyna. This method makes it possible to stably resolve the unstable stiffness behavior of the materials in powder state. Finally, we evaluate the performance of the molded products. The particle arrangement and the deformed state of active materials are solid electrolyte obtained by the series of evaluation process are used to evaluate the macroscopic properties of the battery. The figure on the left side is a simple illustration of the relationship between particle arrangement and performance. As explained once again, the blue active materials store the electricity, and the red solid electrolyte is a pathway for electricity. Thus, the ions are taking the path colored in red and delivering electrical energy into the blue particles. So, if the red path is interrupted in the middle, as shown in the left figure, the ions cannot go deeper than that. So, there will be many wasted particles that do not contribute to battery performance. On the other hand, if the red path is continuous from top to bottom, as in the middle figure, these ions can essentially travel all the way to the blue particles. But since the path is quite undulating, the transport efficiency may be poor. Thus, ideally, ionic paths should be laid out in the grid as shown on the right. But even in this case, if the path is too wide, the volume of the active material cannot take up enough, resulting in smaller electrical capacity. We believe that simulation-based trial and error approach considering these various trade-off will be effective. For example, if you want to see the electrical characteristics, you can apply a potential difference and see not only the internal current distribution as shown in the vector plot, but also evaluate the macroscopic performance such as internal electrical resistivity. The rightmost figure is an example of analysis closer to actual operation, simulating problem such as a breakdown of the good ionic conductive path due to cracks by large expansion or contraction of active materials as it is charged and discharged. Thus, the performance as various batteries can be predicted by FEM analysis with multiscale technology. Let me summarize my presentation. Today, I introduced our unique solution for the analysis of all solid-state battery, which is currently the focus of our research and development efforts. Although performance evaluation can now be performed by multiscale analysis, it is necessary to prepare heterogeneous microstructure that depends on the manufacturing process. So a series of manufacturing process simulation technologies were also introduced in this presentation. I would like to emphasize that it is not enough that each analysis process can be executed reliably. downstream processes are strongly influenced by upstream process. So it is important to link them. We are providing the useful interface to realize it. And the performance of the final products can also be predicted analytically based on the multiscale technology by means of microstructure model obtained from the manufacturing process. Okay, this concludes my presentation. I hope I have convinced you of all the advantages of using our solution. Thank you so much for your kind attention.